In this video, I'm going to talk about what is called as Euler's formula. This is perhaps one of the most used formulas in this course, and it's one of the most useful formulas when dealing with complex numbers. The formula essentially says that if you take a complex number of the form cosine theta plus j times sine theta, this can be thought of as e to the j times theta. Now, I'm going to go ahead and prove this, but before I go ahead and do the proof, I want to talk a little bit about how you are going to likely use this formula in the course. And the thing is, if you look at this quantity called e to the j times theta, that's a very confusing quantity, right? Because what does it mean to raise e to a power which is complex? There seems to be no operational meaning to this. There doesn't seem to be a quantity that is easy to explain as saying, this is what you are doing to e when you raise e to a power j times theta. And in fact, I'll try to show the proof, and maybe some things will become clear when we do that. But the way we are going to typically use Euler's formula in this course is to realize that if you have a complex number of the form cosine theta plus j times sine theta, and you want to do algebra with these complex numbers, if you want to multiply two complex numbers together, you want to divide two complex numbers, things like that, this complex number can be treated as e to the j times theta, where e to the j times theta obeys the typical algebra that you see with exponentials. So to give you a more concrete example, if you had, let us say, two complex numbers, let's say I have a complex number cosine theta 1 plus j times sine theta 1. Let's call this complex number as z1. And let's say I have another complex number z2, which is cosine theta 2 plus j times sine theta 2. And let's say we wanted to multiply these two together. Now, you can clearly multiply them together, but you will see that, you get cross terms. You have to collect all the real terms together, collect all the imaginary terms together, so on and so forth. But what Euler's formula tells you is this. You can think of this complex number as e to the j theta 1. And you can think of this as e to the j theta 2. And if you wanted to multiply z1 and z2 together, this is simply e to the j times theta 1 times e to the j times theta 2. And here we can use the rules of multiplying e raised to j theta 1 times e raised to j theta 2. And we can write this as e to the j times theta 1 plus theta 2, which when you convert back to Cartesian form is cosine theta 1 plus theta 2 plus j times sine theta 1 plus theta 2. So you can see how easy it is to multiply these two complex numbers if you use Euler's formula. All right? That is the operational way in which we will use Euler's formula. Okay. All right, so Euler's formula also tells us that let me write Euler's formula here again. E to the j theta is cosine theta plus j times sine theta. So if I replace theta by negative theta, then we get e to the negative j theta is cosine of negative theta, but cosine of negative theta is the same as cosine theta, plus j times sine of negative theta, and sine of negative theta is the same as negative sine theta, right? So this becomes negative sine theta. So now from these two, you can see that if I add these two equations together, we're going to, the sine theta terms are going to cancel out, and we are going to get 2 times cosine theta on the right hand side. So e to the j theta plus e to the negative j theta is 2 times cosine theta, or equivalently 1/2 of e to the j theta plus e to the negative j theta is cosine theta. Oops. And in the same way, if we subtract this equation from the other, I'm going to get 2 times j times sine theta on the right hand side. So I'm going to get 2 times j times sine theta on the right hand side, and that is equal to e to the j theta minus e to the negative j theta. So if we divide both sides by 2j, we get sine theta on the right hand side, and we get 1 over 2j. So these two formulas also turn out to be really useful in simplifying expressions. You may end up with complicated expressions where you may have a bunch of terms which are of the form e to the j theta and e to the negative j theta, and if we use the fact that e to the j theta plus e to the negative j theta over 2 is cosine theta, we can substantially simplify these things. Okay, so this is how we are typically going to use Euler's formula in this class. And now let's go to the proof of why cosine theta plus j times sine theta can be thought of as e to the j times theta. To prove that, let's quickly go back and recall something that you have learned in your freshman calculus class. Now we know that these trigonometric functions cosine theta and sine theta have series expansions. So this series expansion is the Taylor series expansion for cosine theta around theta equal to 0. It's also called as a Maclaurin series expansion for cosine theta. So it tells you that cosine theta is 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial, so on and so forth. And it tells you that sine theta is theta minus theta cubed over 3 factorial plus you see all the odd powers of theta in sine and all the even powers of theta in cosine. And in the same way, there is also a series expansion for e to the theta. The series expansion for e to the theta is that it's 1 plus theta squared over 2 factorial plus so on and so forth. You have all the powers of theta and you don't have any negatives in the coefficients, right? And in fact, I think this series expansion is the best way to think about what it means to raise e to some power. So for example, what is the meaning of e to the some irrational number, let's say pi, for example, right? One way to think about it is to say that e to the pi, for example, is nothing but a short form for the power series that you would get by replacing theta with pi. Or e to the square root of 2, for example, would be e to the would be a short form for what you get by replacing theta by square root of 2, right? So in that same way, if you think of it that way, then we can think of e to the j theta as the short form for what you would get in the power series by replacing theta by j times theta, right? So when I do that, what we're going to get is we're going to get e to the j theta to be 1 plus j times theta plus j theta squared over 2 factorial plus j theta cubed over 3 factorial plus j theta to the 4 over 4 factorial, so on and so forth. Right? Okay. Now let's try to split this into its real and imaginary parts. So notice that the first term is real. The second term is strictly imaginary. Now the third term, which has j theta to the power of 2, right? What is j times theta squared? That's j squared times theta squared. And j squared is nothing but negative 1. So the third term is actually is negative of theta squared over 2 factorial. And do you see what you have here? You have exactly 1 minus theta squared over 2 factorial. And now if you look at the fourth term here, you're going to get j times theta to the 4 divided by 4 factorial. Now what is theta to the 4? I'm sorry, j times theta to the 4. That's j to the 4 times theta to the 4, but j to the 4 is 1. And so if you collect all the real terms, you're going to get exactly the series expansion for cosine theta. So you're going to get 1 minus, I'm going to try to use a different marker. And then let's collect all the imaginary terms together. They're going to have a common factor j, so let's factor that out. So then we're going to get j times, this term is going to give you a theta. Now notice this term is going to give you a j times j squared times theta cube, and j squared is nothing but -1, so you get theta cube over 3 factorial, and you're going to get theta to the 5 over 5 factorial minus so on and so forth. And indeed, the first term is exactly the Taylor series expansion of cosine theta, and the second term is exactly the Taylor series expansion of sine theta. So this tells you that e to the j theta is equal to cosine theta plus j times sine theta, which is exactly what Euler's formula says. Okay, now I went through the proof just to show you where this comes from, but we're not really going to use a lot about the proof in the class, and I really do want you to get comfortable with this number called e to the j theta. Initially this is a number that's very confusing to people, right? Because you're taking e and you are raising it to some complex number, and it's not clear what that means. And the best way to think about that is to say that is a representation of the complex number cosine theta plus j times sine theta. That is all it is. It is just one way to write this complex number, but writing it this way helps you do some arithmetic with it, and hence it's useful to think of this number in terms of an exponential form, and that's exactly what Euler's formula gives you. Okay. Now, a special case of Euler's formula, let's try to erase this. Let's think about what happens to Euler's formula when theta is equal to pi. When theta is equal to pi, Euler's formula tells you that e to the j times pi is cosine pi plus j times sine pi. And you know that sine pi is 0 and cosine pi is -1. Right? So it tells you that e to the j pi is equal to -1, or e to the j pi plus 1 is equal to 0. So this is just a special case of Euler's formula when theta is equal to pi. Sometimes it's called as Euler's identity. And you can, this is such a simple and elegant formula, right? It has some fundamental constants in mathematics that come in many different fields. Like there is pi. Pi shows up in many different things in mathematics. E shows up. And it's a very nice and simple formula that relates e to the e pi 0 and 1. And in the internet you can see several videos or several articles that tells you that this has been rated as one of the most beautiful formulas in mathematics, if not the most beautiful formula in mathematics. And I believe even Feynman called it one of the most beautiful formulas in mathematics. It's called as Euler's identity.